Hello, welcome to the third lecture in linear algebra series. In last lecture, we had discussed what is system of linear equations and how to find the solutions to those equations. Now, today we will be discussing what are the different types of linear system equations and how to find whether a solution exists or not without explicitly calculating the solution by using something called a rank of a matrix. And we will be defining what is eigenvalue and what is eigenvector and how to find the eigenvalue. Now, we had seen that a system of linear equations can be written in a matrix form where A is the coefficient matrix and X is a variable vector, that is a column vector, and B is the right hand side elements vector. Now, this equation can be if B is, so the general equation is Ax equal to B. If B is a zero vector, then that equation we call it as a homogeneous system of linear equations. And if B is not equal to 0, then that is non-homogeneous system of linear equations. Now, if you observe, if you simply substitute x as 0, then it satisfies that equation. So a homogeneous system of equations has at least one solution, that is a trivial solution, and there might be some non-trivial solutions depending on what is A. And to find whether a solution exists or not and whether it has infinite solutions, we will be using something called a rank of a matrix. Now let us define rank of a matrix. So the rank of a matrix is the maximum number of linearly independent rows or columns of a matrix. How it is denoted by using rank of A or R of A. So it need not be a square matrix. For any matrix you can find rank. Now it can be found by counting the number of non-zero rows in a row echelon form, and we had seen in the last lecture how to convert into a row echelon form when you are finding a solution of a solution of system of linear equations by using Gaussian elimination method. Now, so to find a rank of, so example, how to find a rank of a matrix? Let us consider this matrix A 1 2 3 2 3 4 and 3 5 7. Now converting into a row echelon form is, you consider the main diagonal elements, and that main diagonal elements and all the elements which are below that main diagonal elements, you should make them as 0. Now consider the first main diagonal element 1 and make the elements 2 and 3 0. To do that, we are allowed to perform some elementary row operations. Swapping of two rows, or adding multiples of one row to another, and multiplication by a scalar factor. Those are the operations that are allowed, elementary row operations. Now here what we are doing is adding multiples of one row to another. That's the elementary operation that we are doing. To make this 2 as 0, just multiply row 1 elements with 2 and then subtract from R2. So that is R2 minus 2 R1. Similarly, we do R3 minus 3 R1, so that these two elements will be 0. Now if you do on all elements of the rows of row 2 and row 3, we are going to get this matrix. Now again we consider the second row second element. We consider second row second element. All the elements below that we should make 0. So for that we have to do one more transformation on R3, that is adding multiples of R2 to R3, that is R3 minus R2. If you do, then we are going to get because here also we have minus 2, minus 2, minus 2 will cancel out. And we have, so now we just have to count the number of non-zero rows. So there are two non-zero rows, that's why the rank of a matrix is 2. Okay. And now how this rank is useful in knowing how many solutions are there. So we have to know one theorem called Cauchy-Shapley theorem. What it says is that when you have system of linear equations, Ax equal to b, and it has at least one solution if and only if the rank of the coefficient matrix is equal to the rank of the augmented matrix. The rank of A is equal to the rank of the augmented matrix, then only we have at least one solution. So it can be written in more general form, like let n be the number of variables, and when the rank of A is equal to rank of augmented matrix and it is equal to the number of variables, then you have a unique solution. Similarly, when rank of A is equal to rank of augmented matrix and it is less than n, that means there are some linear dependent rows or two equations which are dependent on another. So in that case, we get a infinitely many solutions. When rank of A is not equal to rank of augmented matrix, then there is no solution. So let us see some examples. Here we have two equations, x plus y equal to 3 and 2x minus y equal to 0. Now the augmented matrix is 1, 1, 3, 2, minus 1, 0. We can find both ranks if we convert this into some row echelon form. So as we know that the main diagonal element is 1, and we have to make this 2 to 0. To make that, we have to apply the elementary row operation, that is adding multiples of one row to another, that is R2 as R2 minus 2R1, then we will get this. Now you can see that the number of non-zero rows are 2. So the rank of A is, when you consider this 1, 1, 0, minus 3, the rank of A is 2, as well as the rank of augmented matrix is also 2. So it is equal to the number of variables, that is the number of variables are 2 here, x and y. So the system is consistent and it has a unique solution. And similarly, we have another equation, x plus y plus z equal to 1 and 2x plus 2y plus 2z equal to 1. Now we get an augmented matrix here, 4 1s, 4 2s, and when you convert into a row echelon form, that is this 2 we have to make it 0 because we consider this main diagonal element 1, and so it is simply R2 as R2 minus 2R1. Then we get, because the number of non-zero rows here is 1, so the rank of A is 1 as well as rank of augmented matrix is also 1, and which is equal, which is less than the number of variables. The number of variables is 3. So this system has infinite solutions. And another example, we have two equations, x plus y equal to 3 and 2x plus 2y equal to 7, and we have an augmented matrix 1, 1, 3 and 2, 2, 7, and similarly convert into a row echelon form, we get the rank of A as 1 and rank of augmented matrix as 2, and which is not equal. That means the system is inconsistent because we are applying the same transformations on these coefficients as well as the right hand side, and one of them is 0 and the another is not 0, means the system is not consistent and has no solution. So this is how one can use the rank to say about the number of equations of, the number of solutions of a system of linear equations. Okay, so the next is what is eigenvector and eigenvalue. So eigenvector is x here. So for a square matrix, you consider some non-zero vector is an eigenvector if multiplying by A, that means doing some transformations with A, results in a new vector that is just a scaled version of X. That means here lambda is a constant. So you are doing some transformation of X by using a matrix A, and we are getting some scaled version of X. Then this X, we call it as a eigenvector. Okay, and the lambda, the constant factor, we call it as a eigenvalue. So this is the fundamental equation, that is we call it as Ax equal to lambda x. Now what is the geometric interpretation? So eigenvector, you consider it as a special vector. When we are doing transformation with X, it maintains its direction, but it is simply either stretched or shrunk or flipped during the transformation. Something like when you say lambda equal to 2, so when you do a transformation with Ax, you get 2 into x. That means the vector is doubled its length, but there is no change in the direction. When you say lambda equal to minus 1, it's flipped to point in the opposite direction. So that is the significance of this eigenvalue and eigenvector. Now, how to find the eigenvalues? So you have the basic equation Ax equal to lambda x. Now we can write Ax equal to Ax minus lambda x equal to 0, and you get A minus lambda I into x equal to 0. Now if you, I think if you observe carefully, if you have some value for lambda, then it is like a homogeneous system of linear equations. Now, so, and as you know that this has one trivial solution, that is x 0, but we are interested in x non-zero. So when a x non-zero exists, this matrix must be a singular matrix. That means the determinant must be equal to 0. So you just calculate the determinant and then equate it to 0. Whatever the equation that you get, that we call it as a characteristic equation of a matrix. So finding lambda from that characteristic equation is like finding the eigenvalues. So you consider this matrix A. Now we have to write the characteristic equation, that is the determinant of A minus lambda I equal to 0. So now we have A minus lambda I is 2 minus lambda 1, 2 minus lambda. Now you equate it to determinant of A minus I, equate it to 0. Then if you do simplification, then you get lambda square minus 4 lambda plus 3 equal to 0. When you solve this quadratic equation, you get 2 eigenvalues. It is a 2 by 2, that's why we got 2 eigenvalues. If it is a 3 by 3, we might have got a cubic equation, and then we might have got 3 eigenvalues. And in the next lecture, we will be discussing how to find the eigenvector. Simply substituting this lambda there in the original equation, Ax equal to lambda x, and from there, as we know that A minus lambda I into x equal to 0, it will become a homogeneous equation. Then we can find out what is x, and that gives you eigenvector. And then we will be discussing some properties of eigenvector and eigenvalues in the next lecture. Thank you.